Hi everyone, this is a feedback video for the mock exam that you sat on the 24th of April. In this presentation I'm going to go through each question in turn, so you don't have to watch the whole presentation if you don't want to. It's probably going to be quite long, so just skip forward to the questions that you want to get feedback on if that's your preference. So we'll start with section A, and these are the shorter questions. So in question 1, you are asked to give the full electron configuration of the following elements and ions, and you're given 3 of them. You've got elemental aluminium, an iron 2+ ion, and a chloride ion with 1 negative charge on it. So for each of these, the best thing to do is consult your periodic table, find their atomic number, and from that you'll be able to work out how many electrons you would have around the atom if it's in elemental state. So for aluminium, that's quite nice and easy. Aluminium is atomic number 13, and then you fill up your electron orbitals by the standard method, and you'll see that the configuration there is 1s2, 2s2, 2p6, 3s2, 3p1. Count your electrons there should be 13 of them. Then we have iron 2+, so the 2+ tells us that it has lost 2 electrons from its standard configuration. You should also note that iron is a transition metal, and that means it's going to lose electrons from the 4s orbital first. And so iron 2+'s configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. It's d6 because if you look at where it is in the D block, it is the 6th element along on that first row. So we'll have 60 electrons, and it will have lost its 2 4s electrons. And then we have chloride, Cl-. The minus sign tells us that it has gained an electron. And if we look at where chlorine is, it is element 17, or atomic number 17, and so that means it would have 17 electrons normally, but it's gained one, so it must have 18. So we can fill up our electron orbitals like so, and it should be 1s2, 2s2, 2p6, 3s2, 3p6. Again, check your electron count, make sure that it is 18 there. Now, this question overall is worth 3 marks. That's 1 mark for each of the different elements or ions that you had to give the configuration for there. Note that it does say in the question you have to give the full electron configuration, and that's what I was expecting to see. If you gave the noble gas configuration and you only gave the noble gas configuration, then this would have been marked as incorrect. However, if you defined what your noble gas configurations were first, then I would have accepted the noble gas configuration for these elements or ions. In question 2, you're asked to give the equation for the first ionization energy of beryllium. So, first ionization energy tells us that it is losing an electron to form a cation. If you look at beryllium, its symbol is Be in the periodic table. And here is the correct answer. It's beryllium, 1 atom of beryllium in its gaseous state, and then it is losing an electron. And so on the right-hand side of the equation, we have our beryllium cation, Be+, still in the gaseous state, plus 1 electron. And this is the correct way to write an equation for a first ionization energy. No minusing of electrons, no solids going to gases. Atoms should already be in their gaseous atomic state. In question 3, you're asked for how many grams of oxygen are there in 0.830 grams of propanoic acid. This question is worth 3 marks, and that tells you there must be 3 key steps to solving it. The first of these is to work out the molecular weight of propanoic acid. So, given the name propanoic acid, you should be able to work out that the formula of it is C2H5COOH, and then using the masses given in your periodic table, you should come out with a molecular weight of 74.08 for propanoic acid. The second step then is to work out what fraction of this mass is oxygen. So there are 2 atoms of oxygen in each molecule of propanoic acid. So we can do 2 times 16, that's the mass of oxygen given in your periodic table, divided by 74.08, and that will give you a decimal fraction of 0.432. We can then take this decimal fraction and multiply the mass of propanoic acid that we started with, so 0.830 grams. We can multiply this by 0.432, and that will give us 0.359 grams of oxygen in our 0.830 grams of propanoic acid. Question 4 is an IUPAC naming question. You're asked to give the IUPAC names for the 2 molecules that are shown below. So we'll look at the molecule in part A first. First thing you want to do here is work out the root of the name. How many carbons are there in the longest chain? So if you count the carbons there, you'll find that there are 5, and that tells you it must have pentan in its name. We then want to look at the functional groups that are on there. Which ones have the highest priority? Well, we have an alcohol group and an amine group, and if you remember your naming priority, you'll know that the alcohol has the higher priority, so this compound must be an alcohol. And so it is pentan 2-ol, because our alcohol group is on the 2nd carbon along the chain, and because the alcohol is high priority, it will have the lowest number on there. We then need to incorporate the amine group into this name, so we'll have to use this as a prefix, so that's going to be amino, and our amine group is on the 3rd carbon along the chain, so it will be 3-amino-pentan 2-ol. Now let's look at the molecule in part B. So again, let's work out the length of the longest carbon chain first here. Relatively easy, this one is 6 long, so it's going to have hex in the name. Should also look at the functional groups here. We have an alkene and we have a ketone as well. So the ketone takes priority over the alkene, but we still need to put the alkene in the name. So if it's a ketone, it's going to end in -one, and that ketone is on the 2nd carbon along, so it's going to be 2-one. But our alkene, instead of being a prefix, it fits into the name after the hex, so it's hexene-one, but with the numbers in there, the alkene starts on the 4th carbon along, so it's hex-4-ene-2-one. Now, you'll notice that there's still a hyphen in front of the hex there. That means there is another part to this name, and that is identifying the stereochemistry that we have around the alkene bonds in there. Is it E or is it Z? Well, if we look at the groups that come off of the carbon-carbon double bond, we have 2 hydrogens that are implicit in there and 2 parts of the carbon chain. The parts of the carbon chain are going to take priority over the hydrogens, and those carbon chains carry on opposite sides of the double bond, and so this is E. So they are opposite one another, they are antigagon, so this is E hex 4-ene-2-one. In the first question here, it was worth 2 marks, so that's roughly half a mark for each main part of the name. And in part B, it's worth 3 marks. There is 1 mark for identifying the stereochemistry, and then again about half a mark for each other part of the name there. Question 5, you're asked to give 2 physical properties which are typical of ionic compounds. You could have had any one of the following here. You could say that they have high melting and boiling points, that they conduct electricity in solution or as liquids, that they are typically solid at room temperature, or that they are soluble, usually in water. Question 6. An electrochemical cell containing a zinc half cell and a copper half cell was set up using a potassium nitrate salt bridge. And you're given the 2 half equations here for both zinc and copper, and the potentials for each of these cells. And in part A, you're asked to draw this cell using the conventional representation. So this is the representation where you have both the electrodes as solids and then their ions that are produced, separated by phase boundaries and salt bridges. And to decide which one goes on the left and which one goes on the right, you want to look for the one that has the more negative cell potential. So in this case it's zinc. So this tells you that zinc is going to be the anode, and it's where the oxidation is going to occur. So zinc is going to go from being solids to being cations, whereas at the cathode, copper is going to be reduced from copper 2+ to copper metal. So copper is going to go on the right, and we can draw this using the conventional representation. So you have zinc solid, single straight line representing phase boundary, zinc 2+ aqueous, double vertical line representing the salt bridge, copper 2+ aqueous, single line, copper solid. Then in part B, you're asked to determine the standard potential for this zinc copper cell. So this is always cathode minus the anode value, so the more positive value minus the more negative value. So here we have 0.34 volts corresponding to the copper cell minus 0.76 volts corresponding to the zinc cell, and together that gives you an answer of plus 1.10 volts. Part B is worth 2 marks. That's 1 for understanding that it's cathode minus anode, and then 1 for getting the correct value of the cell potential there. Question 7. The structures and boiling points of propane and fluoroethane are given below. Identify the intermolecular forces that would be present in a sample of each compound and explain why fluoroethane has a higher boiling point than propane. Propane is shown on the left with a boiling point of 231 Kelvin. Fluoroethane is shown on the right with a boiling point of 236 Kelvin. So first thing you might notice is that one of these has 3 carbons in it, that's propane, and a lot of hydrogens, whilst fluoroethane has only 2 carbons in it and then 1 fluorine. So actually it's a much smaller molecule, and yet it has a slightly higher boiling point. So there must be different intermolecular forces at play here to give fluoroethane a higher boiling point, despite the fact that it is smaller. So you want to think about your intermolecular forces, and if you think about this, you realise that, well, both samples are going to have London dispersion forces, which are the temporary and induced dipoles present between their molecules, and those are going to form within the carbon chains. But additionally, fluoroethane will have a permanent dipole, and that's because fluorine is very electronegative, and it's going to pull electron density towards it, and that's going to create a permanent dipole in our fluoroethane molecule. And this is going to allow molecules of fluoroethane to interact by dipole-dipole interactions. These dipole-dipole interactions are stronger, so that means that it's going to take more energy to separate our fluoroethane molecules, and so it's going to have a higher boiling point than propane. Question 8. Draw an appropriate illustration of the polymer made from 1,4-butanedioic acid and 1,4-butane-diamine. So the first thing you might want to do here with this question is to actually work out what the structures of 1,4-butanedioic acid and 1,4-butane-diamine are. So one of them is going to be a carboxylic acid that's given away by the oic acid, and the other one is going to be an amine given away by the amine in its name. They also have a di in both of them, which means that they're going to have 2 of each of their respective groups, and in both cases they're at the 1 and 4 positions of the molecule. Both of them have butane in, so that means it's going to be 4 carbons long, and so these groups are going to be the end of these carbon chains. And so 1,4-butane-dioic acid and 1,4-butane-diamine look something like this, with the dioic acid on the left and the amine on the right. So then you want to think about how these two are going to react together to form this polymer. We have an acid group, we have an amine group, and you should know that if those react together, those will form an amide bond. And so we can now see this amide bond in the middle of this structure here. So this is a section of the polymer that is made from 1,4-butane dioic acid and 1,4-butane diamine. You'll note that it's only got the one amide bond shown and that it still has a carboxylic acid group and an amine group at either end of this structure, but these are outside the brackets, and at the bottom of the brackets we have an N, and that represents the fact that there are going to be a lot of these repeat units in this polymer. Question 9. Solutions of nickel 2 ions with the monodentate ligand H2O. And then you've got the formula NiH2O62+ are green in colour, whereas those of nickel 2 ions with the bidentate ligand 1,2-ethylene diamine, En, with formula NiEN32+, are violet in colour. Part A, explain why solutions of transition metal ions such as those above are coloured. So the sort of answer that we're looking for here is to say something along the lines of absorption of light frequencies causes electrons to jump to higher energy levels. Complementary frequencies are reflected or transmitted. Or you could say that DD transitions absorb light, referring to the specific type of transition that's involved here. Then in part B, you're asked to explain why the colours of the two different ions are different. And this goes to the idea of crystal field theory. So you want to be saying something along the lines of the crystal field strength of the ligand changes the size of the gap between the low and high energy d orbitals. This changes the wavelength of light absorbed and hence the frequency that is reflected. So in this case, water is a weak field ligand and ethylene diamine is a strong field ligand. As long as you got something along the lines of saying that the crystal field strength changes the size of the gap and that it changes the wavelength, you would have got the full 2 marks there. You don't need to specify that H2O is a weak field ligand and that En is a strong field ligand. Question 10. Draw and name 2 structural isomers with molecular formula C3H6O. So you've got quite a bit of freedom with this answer here as to what you could give. If you try and think about arranging 3 carbons, 6 hydrogens and 1 oxygen, there are a number of different structures you could come up with. So you only need to get 2 of them. So any 2 of the following would have been suitable. So the ones that I thought you were most likely to get here would be propan-2-one, propanal, Z-prop-1-ene-1-ol, or E-prop-1-ene-1-ol. Obviously, propan-2-one and propanal are a bit easier to name than the other 2. So it's likely that you got 2 of these 4, but if you came up with any other structure that fitted this criteria, I would have also given you the marks for that. Question 11. How many moles are there of calcium sulfate in 690 milligrams of the compound? So the way you want to go about solving this question is to first of all work out what the molecular weight of calcium sulfate is, or the molecular mass, which is 136.15 grams per mole if you go off the numbers that are given to you in your periodic table. Now we know the molecular mass and we know the mass of the compound that we have. We can work out the moles. We just have to remember to convert the 690 milligrams into grams. So 690 milligrams is 0.690 grams. Divide that by the molecular mass, 136.15 grams per mole, and that will give you 0.00507 moles, or 5.07 times 10 to the minus 3 moles. Question 12. The reaction between hydrogen bromide and oxygen occurs as represented by the equation 4HBr plus O2 to give 2H2O plus 2Br2. The rate equation found by experiment is rate equals K multiplied by the concentration of HBr multiplied by the concentration of oxygen. Explain why this reaction cannot be a one-step reaction. So the clue here lies in looking at the rate equation and then comparing it to the actual reaction equation. And so if you look at the rate equation, you'll see that it's first order with respect to both HBr and O2. And this will show you that in our rate determining step, there's only one molecule of each of those present. But the key one here is HBr. If you look back at the reaction equation, there are 4 molecules of HBr involved. So somewhere there must be additional steps in this reaction that are not rate determining steps that involve the other 3 molecules of HBr. So in your answer you wanted to identify that HBr was first order, and that means there's only one of them in the rate determining step, and then that because the overall equation has 4 molecules of HBr in it, there must be additional steps in this reaction. Question 13, part A, you're asked to draw the mechanism for the electrophilic addition of bromine and but1-ene. So first of all, you want to draw out your reagents here for this mechanism. So here's but1-ene on the top, and there is bromine, which in this case is Br2. And here we've represented it as being 2 Br molecules joined together by a single covalent bond. So you're drawing the mechanism for an electrophilic addition. And in an electrophilic addition, you are going to have, first of all, the electrons in the pi bonds are going to push down to attack one of the atoms of bromine in the dibromine. And that's also going to cause the bond between our 2 bromines to break, and the electrons will push onto the bromine that the electrons from the but1-ene are not being pushed towards. So that's going to result in 2 charged species. We're going to have a bromine anion and then this organic cation with a positive charge on one of the carbons. If we have a positive charge and a negative charge is going to be attracted towards positive charge. So the electrons surrounding bromine, or the pair of electrons represented by that negative charge, are going to push towards the positive charge, and that's going to result in a covalent bond being formed between the carbon and the bromine. And then you'll get your product, which has a bromine on the first carbon and a bromine on the second carbon. Then in part B, you're asked to name the product of the above reaction, and as I've just said, we have a bromine on the first carbon, bromine on the second carbon, so that's going to be 1,2-dibromobutane as the name of this product. Question 14, part A. You're asked to calculate the concentration of a solution of potassium hydroxide, KOH, that has a pH of 12.7. So this question relies on you remembering that pH plus POH equals 14. This is potassium hydroxide. It is a base. We are trying to find the concentration of this, but in doing so we're finding the concentration of the hydroxide ions, not the hydronium ions. So we want to find the POH really of this solution first. So to find POH, we're going to do 14 minus 12.7, and that will give us 1.3. We can then, to find the concentration of hydroxide, which will be the same as the concentration of potassium hydroxide, as potassium hydroxide is a strong base, we can do 10 to the power of minus POH, so 10 to the power of minus 1.3 gives us a value of 0.05 molar as the concentration of this potassium hydroxide here. Then in part B, you're told that a solution of sodium carbonate, Na2CO3, prepared to the same concentration as the above potassium hydroxide solution, so concentration of 0.05 molar, has a pH of only 11.5. Explain why this solution has a lower pH. So as mentioned in part A, we can identify potassium hydroxide as a strong base, and you might know or be able to work out from this question that sodium carbonate is a weak base. So it only partially dissociates in water, so it's going to result in a lower concentration of hydroxide being formed. So there's less hydroxide despite the same concentration, so therefore you will have a lower pH as you don't have as much hydroxide present. Question 15. Magnesium carbonate decomposes to form magnesium oxide and carbon dioxide. You are given the reaction equation there, and you're also given some thermodynamic values. You are given the enthalpy change, which is 117 kilojoules per mole, and the entropy change, which is 175 joules per Kelvin per mole. And you are asked in part A to determine if this reaction will occur spontaneously at a temperature of 550 Kelvin. So spontaneity of a reaction is linked to its value of Gibbs free energy. Gibbs free energy, delta G, is calculated from delta H minus T delta S, so the temperature that the reaction takes place at multiplied by the entropy. And so to find the delta G for this reaction, we need to plug our values into this equation. First, we need to convert those kilojoules in the enthalpy change to joules to put them into the same units as our entropy. So that's going to be 117,000 joules minus 550 Kelvin multiplied by 175 joules per Kelvin per mole. And that gives us a value of 20,750 joules per mole, or 20.75 kilojoules per mole. This is a positive value of delta G. Positive value of delta G means that a reaction would not be spontaneous. For a reaction to be spontaneous, our value of delta G needs to be either 0 or negative. Then in part B, you're asked to calculate the minimum temperature at which this reaction does actually become feasible, at which temperature does it become spontaneous. So again, this is using the idea of delta G equals delta H minus T delta S. And at temperature feasibility, delta G must be 0. And so, therefore, the temperature of feasibility we can find by rearranging the equation such that T equals delta H divided by delta S, because if delta G is 0, we can find temperature simply by dividing delta H by delta S. And so we can take our enthalpy change in joules, so 117,000 joules, divided by our entropy change, 175 joules per Kelvin per mole, and that will give you a value of 669 Kelvin as the temperature at which the reaction becomes feasible. Question 16. The mass spectrum of a ketone is given below. So there is your mass spectrum. And in part A, you're asked to suggest formulas for the fragment ions labelled X and Y. So firstly, you want to think about the fact that this is a ketone, and that probably means you're going to get an acylium ion as your most stable fragment in there. So if we take a look at our base peak, the one that's tallest on there, the one that is labelled X, you'll see this has a mass charge ratio of 43. So most stable fragment is most likely to be an acylium ion. It has a mass charge ratio of 43. Should be able to work out that that fragment looks something like this. So with 2 carbons in there and our carbon triply bonded to an oxygen in this acylium fragment. Then we can look at Y, and this has a mass charge ratio of 57. So if you want to think about what could sum up to give you a mass charge ratio of 57 or a mass of 57, a good candidate for this would be a butyl fragment. And so you want to suggest the formulas for these, not just the structures though, so you want to convert those into their formulas. So X is CH3CO+, and Y is CH3, CH2, CH2, CH2+. And in part B, you're asked to draw the structure of the ketone. If you look, the molecular ion, so the peak that corresponds to the molecule with just a positive charge on it, so it's just had an electron knocked out, is at 100. And quite conveniently for you in this question, 43 plus 57 equals 100. So you can imagine just joining together this acylium fragment and the butyl fragment, and that will give you the structure of the ketone. So it has 6 carbons in its chain and the ketone group on carbon 2. So it's hex 2-one. And then in the final question of section A, question 17, you're told that a mixture of ethanol and cyclohexane is run through gas chromatography apparatus. And in part A, you're asked to describe what happens to the mixture in the apparatus. So for this, you need to understand how GC works, and your answer should be something along the lines like this. So first of all, you want to say that a mixture is heated to vaporize it and is then carried onto the column by the carrier gas. It's gas chromatography after all. There has to be a gas involved in there somewhere. The two components are then absorbed onto the stationary phase, then they evaporate into the mobile phase, repeating this process and gradually travelling to the end of the column. So in chromatography, you should remember that you have a stationary phase and a mobile phase. The mobile phase in gas chromatography is the carrier gas, and the stationary phase is either a solid or a liquid that is stuck to the column. And so your mixture is adsorbed onto the stationary phase or into the stationary phase if it's a liquid, and then the heat of the oven of the gas chromatography apparatus evaporates it back into the mobile phase. It's carried along for a bit until it is readsorbed, and this process repeats, and the components gradually travel to the end of the column, separating out as they go. Then in part B, you're told that the ethanol and cyclohexane are eluted from the apparatus at different times after injection. What causes this to happen? Well, it's the basis for all chromatography. It's that different components will separate depending on their adsorption strengths to the stationary phase, which is the principle in all chromatography, and in gas chromatography you also have the added factors of their boiling points. So if they have different boiling points, one will evaporate more readily than the other, and that's also going to be dependent on the column temperature, whether it's a very hot column or a slightly cooler column. So you need to mention all 3 of those points in order to get the full mark for part B here. And now we move on to section B, the longer questions in the paper. So in question 1 of section B, you're told to start off with, if iron powder is added to a solution of copper sulfate, the following redox reaction will occur. Then you have a reaction between iron and copper ions, leaving you with iron ions and solid copper. And in part A, you're asked for which species is oxidized and which is reduced, explaining your answer. So you should recall that oxidation is loss of electrons, reduction is gain of electrons, and if you look at the equation, you will see that iron is oxidized because it loses electrons, going from iron in elemental state to iron 2+, so it is lost 2 electrons, whilst copper is reduced because it goes from copper 2+ to copper elemental state, it has gained 2 electrons. Then in part B, you're told that the enthalpy change of reaction, delta H reaction, can be determined by measuring the temperature change, delta T, of the reaction above. To do this most accurately, the reaction should be in an isolated system. What is meant by the term isolated system? So this is a recall of a definition, and that definition that you're trying to recall is a closed insulated vessel which cannot transfer either matter or energy to its surroundings. Then in part C of question 1, you're told that the reaction was carried out by dissolving 2.5 grams of copper sulfate pentahydrate, CuSO4 5H2O, in 100 grams of water, followed by addition of 3 grams of iron powder. Part I here is what is the concentration of the copper sulfate pentahydrate solution. So to work out concentration, which will be in moles per litre, you're first going to need to know the moles of copper sulfate pentahydrate that you used. So you'll first need to calculate the relative formula mass here, as this is copper sulfate with 5 waters in there. So the relative formula mass here you can calculate from the values given in your periodic table, remembering that it is 5 waters, not 5 hydrogens and then 1 atom of oxygen, but 5 waters. And so the relative formula mass here would be 249.69 grams per mole. Now you know the relative formula mass, you can calculate the number of moles of copper sulfate pentahydrate that were taken, which is 2.5 divided by 249.69 grams per mole, and that will give you 0.010 moles. Now you know the moles, we need to work out the concentration. We have the moles, we have the mass of water that was used. We can convert that mass relatively easily into volume. As you know, it is 1 gram of water is 1 milliliter. And if you have 100 milliliters, that's 0.1 liters. So that is 0.010 moles divided by 0.1 liters will give you 0.10 molar as the concentration. And then in part II, you're told that delta T was found to be 5.6 Kelvin. It is assumed that the specific heat capacity of the reaction mixture is the same as water. Cp equals 4.184 joules per Kelvin per mole. Calculate the heat, Q, that was needed to raise the system by 5.6 Kelvin. So this is a case of remembering how all these values are linked together. Heat, Q, is mass of the system multiplied by the specific heat capacity multiplied by the change in temperature. Lucky for you, you've been given the change in temperature here as 5.6 Kelvin. You've been given the specific heat capacity, which is 4.184 joules per Kelvin per mole. You just need the mass of the system, which is going to be the sum of the copper sulfate pentahydrate, the water, and the iron powder. So mass is 100 plus 3 plus 2.5 grams, multiplied by 4.184 joules per Kelvin per mole, multiplied by 5.6 Kelvin, and that will give you Q, which is 2,472 joules, or 2,500 joules to two significant figures. In part III, you're asked to identify the limiting reagent in the reaction. So you need to work out which of your two reacting species has the lowest number of moles. So first of all, you want to work out how much of the copper cations were present. You already know this, it's the same as the number of moles of copper sulfate from part 1, which is 0.010 moles. You can then work out the number of moles of iron present by taking the mass, 3 grams, dividing it by the atomic weight, which is 55.85 grams per mole, and that tells you you have 0.054 moles of iron present. So clearly there is a lot more iron than there is copper cations present or copper sulfate present, so your copper sulfate must be the limiting reagent here. Then in part 4, you're asked to determine delta H of reaction, the enthalpy change of reaction in kilojoules per mole, and you should possibly remember, and also maybe it was a bit of a clue from parts 2 and 4, being asked to determine the heat of reaction, the moles of limiting reagents, that you need these values to calculate delta H of the reaction, because you can calculate it from your value of Q divided by the moles of limiting reagents, with a minus symbol in front, because Q is the amount of heat that has to be, or that is transferred, whereas delta H is the amount of heat that is given out. So you can do minus 2,472 joules divided by 0.010 moles of your limiting reagent, the copper, and delta H reaction will be minus 247 kilojoules per mole, once you have factored in a joules to kilojoules conversion here. In section B, question 2, part A, you're told that sodium fluoride and sulfuric acid react together in the following overall reaction, where you have sodium fluoride plus sulfuric acid giving you hydrogen fluoride and sodium hydrogen sulfate. In contrast, sodium bromide and sulfuric acid react together in the following overall reaction. So here you have 2 equivalents of sodium bromide plus 3 equivalents of sulfuric acid, giving you bromine, 2 equivalents of sodium hydrogen sulfate, sulfur dioxide, and 2 equivalents of water. And you're asked to explain why the reactions between sodium bromide and sulfuric acid produces diatomic bromine, whilst the reactions between sodium fluoride and sulfuric acid produces hydrogen fluoride. So this requires you to remember something about periodicity, in particular the reactivities of the halogens and their anions. So the answer that is being looked for here should be something along the following lines. Two halide ions, X-, can lose an electron and combine to become the halogen, X2. Down group 7, the halide ions get larger, so it is easier to lose an electron because it is further away from the nucleus and is shielded by the other electrons. The larger halides will therefore more easily lose an electron to form X2. So bromine, being further down the group and being larger, is able to lose an electron more easily to form X2 compared to fluorine, which is right at the top of the group. Then in part B, you're asked to use the data given below, construct a Born-Haber cycle for sodium bromide and hence calculate its lattice association enthalpy. And you're given a lot of data here. We have the enthalpy of formation for sodium bromide, the enthalpy for the atomization of bromine, the enthalpy for the atomization of sodium, the first ionization energy for sodium, and the first electron affinity for bromine. So you want to start constructing a Born-Haber cycle here, so it's probably best to start with the compound that you're trying to make, which is sodium bromide, and that will go down at the bottom, sodium bromide solid. We can get to sodium bromide using one of the values that's been given above, which is the enthalpy of formation of sodium bromide, which represents its formation from the elements at their standard states. So that's sodium as a solid and bromine as a gas. But we want to find the lattice enthalpy here, so we have to go round a bit of a longer way now. So to get to the lattice enthalpy, first we have to atomize our reagents into their gaseous sort of monoatomic states. So first of all, we can atomize bromine, then we can atomize sodium. Now they're gaseous atoms, we want to get to gaseous ions, so we can do the first ionization energy of sodium here to get sodium plus, an electron and bromine, and then we can take that electron and add it onto bromine using the first electron affinity for bromine. And because that value is a negative, instead of going upwards, we're going to go down from that top point there. We now have sodium as a cation and bromine as an anion, and from these we can add them together to form the sodium bromide as a solid, and the enthalpy change we'd see if that occurred would be the same as the lattice enthalpy. This Born-Haber cycle overall is worth 3 marks. That's roughly half a mark for each stage in the cycle. You can then calculate the lattice enthalpy by working backwards from the sodium and bromine ions through the electron affinity, through the ionization enthalpy, through the atomization energies of both of them. And in this case, we're going the wrong way along the arrows, so we invert the sign on each of them, so we put a minus in front of them. And then we're going to go along the arrow the correct way for the enthalpy of formation for sodium bromide, so we can represent that as a plus in this equation here. So we can add or subtract all the values together accordingly, and that will give us a lattice enthalpy of minus 751 kilojoules per mole. Then in part C of question 2, you're told that a group 1 metal halide was heated in a test tube with ethanol and acidified silver nitrate. A pale yellow precipitate was formed, which was found to be insoluble in concentrated aqueous ammonia. The metal halide was also subjected to a flame test, which gave a red flame. Identify the metal halide, briefly explaining your reasoning. So you've been given the results of 2 tests here. The first one is going to tell you the identity of the halogen. The second one is going to tell you the identity of the metal that's in your metal halide. So in the test with ethanol and acidified silver nitrate, we have a precipitate being formed. So that tells us that it's going to be one of either chlorine, bromine or iodine, as fluorine doesn't give a precipitate. We're then told it's insoluble in concentrated aqueous ammonia, so no concentration of ammonia whatsoever is going to dissolve it, and so that means it's likely to be iodine. Then we can go by the results of the flame test, which gives a red flame. A red flame is indicative of it being lithium, so the most likely identity of this metal halide is lithium iodide. Then we move on to section B, question 3. And in part A, you're told that the partially complete synthesis scheme for an azo dye is shown below, and the scheme is there in 3 steps. And there are some compounds that are missing, represented with X, Y, and Z, and in part I you're asked to identify compounds X, Y, and Z. So the easy way to do this is just to look at the equations as they are, see what's missing, and balance them out. Certainly in the case of X, you should be able to identify that the missing compound is sodium nitrate, NaNO2. Y, well, if you look at the scheme in step 2, you'll see that on the product side there is this azide compound there, big aromatic ring in it, and you might remember that azide compounds are formed from the reactions between aromatic amines and HNO2. And you can see that that azide, where the azo group is, the double nitrogen group, that would be where the NH2 originally was, and that sodium sulfate group would probably be existing still in the starting reagent. And then for Z, well, it's an azo dye synthesis. Z is going to be the azo dye. You're going to take the azo compounds that you made with the azo group on, and then that's going to react with the other aromatic compound that's present, and is going to produce something that looks a bit like this. Then in part II, you're asked to give a suitable temperature for step 2 to be performed at, and explain why temperature control is important in this step. So this question requires you to remember something about the synthesis of azo dyes, and that's that you really want to be doing these reactions between a temperature of 0 to 10 degrees Celsius. Because temperature control is important, as at warmer temperatures the product will be a phenol rather than a diazonium salt. Or you could say above 10 degrees that the diazonium salt tends to decompose to give a phenol. Then in part B of question 3, you're told that the proton NMR spectrum of another azo dye is shown below. The doublet peaks at 8.2 and 6.8 parts per million are due to the protons on the amine substituted aromatic rings. So then you're showing the NMR spectrum and the structure of the azo dye above it. And in part I, you're asked to explain why the peaks at 8.2 and 6.8 parts per million are doublets. So these are the two that are picked out for you in the question. You should be able to see them in the NMR spectrum. And they're described as doublets, which means that they are split into 2. And the reason this happens is because they are on carbon atoms which have 1 hydrogen on the adjacent carbon atom, and this leads to doublet splitting. So those peaks correspond to the protons on the amine substituted aromatic ring. That's the aromatic ring on the right of the structure. Those protons are the ones that are implied. They're not shown, but they are there on the aromatic ring. And on the neighbouring carbons that are next to them, one of those carbons is going to be taken up with a bond to a nitrogen, so it has no bonds to protons, and the other carbon next to it is going to have a bond to a hydrogen. So there's only 1 hydrogen on the adjacent carbons there. Then in part II, you're asked to assign the remaining 4 peaks at 8.5, 7.6, 5.3 and 2.3 ppm based on their splitting patterns and chemical shift values. So if you take a look at the structure, you can see that there's an amine group that still needs to be assigned, there is a methyl group on the far left that needs to be assigned, and there are protons on the aromatic ring on the left that need to be assigned. If you also look at that aromatic ring, you'll note that it has para-substitution, that the substituent groups on it, the azo group and the methyl group, are exactly opposite one another. So that means that there'll be 2 different proton environments on that aromatic ring due to symmetry in the structure. So let's assign these peaks now. The peak at 8.5 is a doublet, which tells you there must be one proton on the adjacent carbon. It's strongly de-shielded, being at 8.5 ppm, and that means it's most likely to be an aromatic proton. In fact, this is the one closest to the azo group, but you didn't have to say that to get the mark here. 7.6 is also a doublet. Again, that shows that there must be one proton on the adjacent carbon. Again, it's strongly de-shielded, which is indicative of it being an aromatic proton. Then we have the peak at 5.3, which is a broad single peak. It's not split at all, which means that there are no protons on any neighbouring carbon atoms, but being quite de-shielded shows it must be next to a reasonably electronegative atom or environment, which makes it a good fit for being the protons that are attached to the nitrogen in the amine group. And then finally at 2.3 we have a singlet. Again, that shows that there's no H on the adjacent carbons. This one, being at 2.3, only has relatively weak de-shielding compared to all the other peaks, and that would suggest that it is the protons on the methyl group that is attached to the aromatic ring. So it's close-ish to the aromatic ring, that it's a bit of a higher ppm than we'd expect for a methyl group, but they're still far away enough to not feel very much effect of the aromatic ring. And you've got 1 mark here for each correct identification. Half marks would be assigned if you were partially correct in some cases. And now we move on to question 4 of section B. So you're told that the following Fischer esterification reaction between an alcohol and carboxylic acid is performed with the stated conditions. So you have one equivalent of the alcohol, one equivalent of the carboxylic acid. You have concentrated sulfuric acid present in there, and then it yields an ester and water. Then in A, you're told that at equilibrium there is a 50% conversion of reactants to products. Then in part I, you're asked what is the approximate value of the equilibrium constant Kc for this reaction, explaining your answer. So if you have about a 50% conversion of reactants to products, that means that your value of Kc is going to be approximately 1. And you're going to have, in your equilibrium expression, roughly equal values on top and on the bottom in terms of concentration. And so that's going to give you a 50-50 mix of the products and reactants. And so as Kc is the ratio of products over reactants, this ratio will result in a value of approximately 1. Then in part II, you're asked to suggest, with explanation, how increasing the amount of acetic acid to 6 equivalents will affect the yield of ester and the value of the equilibrium constant Kc. So this links to Le Chatelier's principle. You're going to perturb the equilibrium here by disturbing it, by adding more of one of the reagents. And you should know that by adding more of one of the reagents or increasing the concentration of a reactant, it's going to cause more collisions between reactants, which is going to cause the rate of the forward reaction to increase, such that equilibrium concentrations will eventually become equal to Kc again. So whilst the rate of forward reaction will increase, it doesn't affect the value of Kc. What does happen is that equilibrium shifts towards the product so that the yield of the ester increases. Then in part III, you're told that the esterification reaction is endothermic. How would heating the reaction affect the position of equilibrium and value of the equilibrium constant Kc? So this reaction is endothermic, it wants to take in heat, and you're going to be adding heat to it. So effectively, you are adding a reactant to it. So you're going to increase the temperature, you're going to add heat, and you're going to shift the reaction towards the product. You're going to shift it in the endothermic direction. And in this case, the temperature change favours the products, so the value of Kc will increase. Remember that equilibrium constants are temperature dependent. You change the temperature, you are going to change the value of Kc. Then in part B of question 4, you're told that esters can also be synthesized from the reaction between an alcohol and an acid anhydride. Draw the mechanism for the synthesis of butyl ethanoate from such reagents. So butyl ethanoate is going to be synthesized from butanol and ethanoic anhydride, represented here by a generic alcohol ROH and the ethanoic anhydride. And these are going to react in a nucleophilic addition elimination reaction, otherwise known as a nucleophilic acyl substitution reaction. And in the first step here, the electrons from the alcohol are going to push towards one of the carbonyl carbons in our acetic anhydride, and then the pi bond is going to collapse onto the oxygen there. That's going to result in this species being formed here with a negative charge on one oxygen and a positive charge on the other. The negative charge, or the pair of electrons that causes the negative charge, is then going to push down to reform the pi bond, and in doing so it's going to kick out the leaving group, which is the ethanoate here. And so you can be left with, again, two charged species here. Now the ethanoate, the negative charge there, can be used to abstract a proton from our positively charged species, and that then results in forming the ester and a carboxylic acid product as well. This question is worth 4 marks, and that's about 1 mark for every correct step or every correct stage in this reaction mechanism. And finally, section B, question 5, part A. You're asked to draw a dipeptide that could be formed from the amino acids threonine and leucine, structures shown below. So you've been given the structures of threonine and leucine, and you need to join them together to make a dipeptide. Hopefully you recalled that amino acids can be joined together through an amide bond, or as it's more often known in this case, a peptide bond, to make these dipeptides. So there are 2 possible structures here you could come up with, which are shown here. And if you got either of those correct, then you would have got the mark. Then in part B, you're told that amino acids are the building blocks of proteins. Describe one interaction, including information on the types of amino acid side chains involved, that is used in forming protein tertiary structure. This is a bit of a recall question. You need to think about the interactions that are used in tertiary structures, and you could have had any one of the following. You could have said dipole-dipole, or dispersion forces between nonpolar side chains, such as CH3. Ionic interactions between charged side chains, such as from carboxylate or ammonium side chains. Hydrogen bonding between groups such as alcohols and amines. And disulfide bridges formed between SH groups, so thio groups of cysteine. Or you could have said hydrophobic interactions to form pockets of nonpolar side chains. Any one of those would have got you 2 marks here, provided you gave sufficient description with it. In part C, you're told that enzymes are proteins that function as biological catalysts. Describe the processes that occur in an enzyme catalyzed reactions. 3 marks, there must be 3 steps here. So you need to say something along the lines of, in an enzyme catalyzed reaction, the substrate attaches to the active site on the enzyme. An enzyme substrate complex forms and the reaction occurs. Product or products form and are released. The enzyme can then be used again. That's all you needed to say there to get the full 3 marks. And then in D, you're told that one reaction that can be catalyzed by enzymes is the oxidation of ethanol to ethanal, then to ethanoic acid, and you're asked to draw a scheme to show this oxidation process using an O in square brackets to represent the oxidizing enzyme. So this is worth 3 marks, and it should be relatively easy and straightforward to get all those 3 marks here. So all you have to do is show an alcohol, or show ethanol, oxidized to ethanal, then oxidized to ethanoic acid. And then in DII, you're told that the IR spectrum for one of the compounds in its oxidation process is shown below. Giving your reasons, identify if the spectrum is for ethanol, ethanal, or ethanoic acid. So you want to take a good look at this IR spectrum, and first we'll think, what would you see if it was ethanol? Well, ethanol's an alcohol, so you'd see a broad peak around about 3,000 on the scale there. There's not a broad peak there, so it's probably not ethanol. So that means it's probably ethanal or ethanoic acid. Both of those have got a carbonyl group in. That's going to give a very strong signal around about 1700, which we can see in this case. It's at about 1720 per centimetre on the wave number scale. So it could be ethanal or ethanoic acid. It is in fact ethanal. So as well as having that carbonyl peak at 1720, there are also peaks at about 2800 and 2700 per centimetre on the wave number scale, and those correspond to CH vibrations from the aldehyde group. So this question is worth 3 marks. That's 1 for correctly identifying it's ethanal, and then 2 for giving the fact that it's got the carbonyl peak and then the aldehyde peaks in there as well. And that is the end of this paper.